Welcome back everyone to this lecture on model deployment. As a quick note, when we discuss deployment in this lecture, we're merely talking about loading and saving the model for future use. Towards the end of the course, we're going to have a deeper discussion on how to deploy the model in something like a Flask web application. But for right now, we're just going to consider saving and loading our model as deployment. So in general, we're almost done with our first machine learning run-through. Let's quickly review what we've done so far in the machine learning process. Recall that the supervised machine learning process looks like this. You take in your data, choose your features and label, split it into a training set and test set, fit and train your model on the training set, and then evaluate performance on the test data set. After that, you adjust as needed and then deploy the model. So far, we've done everything kind of in the first half. We've discussed the features and label, split into training sets and testing sets, then we fit and train the model into the training set, and then we evaluated performance on the test set. We also took the additional step to take a look at the residuals and understand that the data was a valid choice for linear regression. So with that being said, the next step would technically be to adjust the hyperparameters of the model as necessary. But right now, we actually don't know quite enough about linear regression to really adjust anything. So later on, we will be exploring polynomial regression, which allows us to adjust the hyperparameter of what order of polynomial we're looking at. And we'll also take a look at regularization, which has its own coefficient values, as well as different types of regularization, like elastic net versus lasso. So those will all be future model adjustments we can perform on top of linear regression. Right now, we're basically going to skip the step of adjusting the parameters, and instead, we're going to pretend that we've been fully satisfied by the test metrics for the performance. And in that case, the next step would be deployment. And in this simple deployment, we're just going to say that we save the model, load it, and then apply it to new data. Let's see all of this in action by heading over to a Jupyter Notebook. All right, here I am back at the Jupyter Notebook. Recall in the previous lecture, we took a look at the residuals, and based off the residual plot, we decided linear regression was a valid choice. There was no clear curve or pattern here. It does look pretty random. And then, more importantly, we decided through some method that these performance metrics are good enough for us. Maybe you talk to your boss, your coworker, your colleagues, or you just took a look at the previous models that people have developed. And for right now, we've decided that these metrics of mean absolute error and root mean squared error are good enough that we're ready to retrain the model on all the data and deploy it to the real world. To do that, we're going to scroll all the way back to the bottom here. And since we're ready to deploy the model, we're satisfied with the performance metrics on the test set, which means I'm going to create a new model instance and call it linear regression. And in general, this should basically be the exact same model type with the same parameters as your model that you adjusted or kept adjusting for optimal performance on the test set. In our case, we haven't really adjusted anything, which is why it looks exactly the same as our very first model. So we create this final model, and then for the final model, we fit it on all the data. Because at this point, we've decided that these model hyperparameters are good enough on a test set, so when we deploy it to the real world, we want to take full advantage of the entire data set, which is the full X and Y. Notice this is not Xtrain or Xtest, it's the full data set from the beginning. So after you run that, you get back the model, and we're essentially pretty much done here. We just need to save it and load it. Something I'm going to do is just show you, or try to show you visually, how the model is fitting to the 3 separate advertising channels, as well as trying to understand the coefficients of the model. Let's start by understanding the coefficients, and we're going to start by just checking if they intuitively make sense. These are the beta coefficients of the linear regression model. I can actually grab these by calling 𝒂𝒓_. And if you want, you can just hit tab off your final model to get a list of all the attributes available to you. But the one we're going to be looking at is this 𝒂𝒓_, and this reports back the actual beta coefficients. And they come in the same order as the feature data frame that you passed in, which means this is the coefficient for TV spend, this is the coefficient for radio spend, and this is the coefficient for newspaper spend. Now, We will dive into the details of what these numbers actually mean, but the one that's easiest to understand just intuitively right off the bat is the coefficient for newspaper spend. Notice that it's almost zero. It is technically a very small number, negative 0.001, but let's kind of pretend for right now that this is basically zero. What does that actually mean in terms of the linear regression model? If it was a pure zero, that means regardless of what you spend on newspaper advertising, the model thinks it doesn't even matter and it's just going to give it a weight of zero, meaning it's going to completely cancel out any value that you spend on newspaper advertising. In fact, it's actually going to lower your total sales because this is technically a very small negative number. Does this intuitively make sense given what we know about the relationship between newspaper and sales? Recall, at the very beginning of this lecture series, we went ahead and showed a plot of newspaper spend to sales. And we saw there was no real relationship here. It almost looks random. And it looks like our final model also thinks that there's no real relationship between newspaper spend or sales. So what it's done is it's just given it a beta coefficient of 0, saying don't even consider newspaper spend. It's kind of not worth the effort. It's just 0 for your beta coefficient. For TV spend and radio spend, that we can see visually, it does look like it has a positive relationship. We scroll all the way back down, and we see here that these coefficients are positive for both of them. And it looks like it thinks radio spend has a bit of a greater effect. Now, what does this actually mean as far as quantitative understanding of these coefficients? Well, if we took a look at one of these coefficients, such as just TV spend, which is 0.045, that means, quantitatively speaking, if you were to hold the other features fixed, so if you hold radio fixed and newspaper fixed and only adjust TV, every time you adjust TV by 1 unit, that is a 1 unit increase in TV spend, so that's technically $1,000 if these units are $1,000. So if we go from 230 to 231, holding radio and newspaper fixed, that means we would expect an increase of 0.045 in sales. So again, the coefficients basically mean, if they're positive, that an increase of 1 unit of that particular feature results in an increase of 0.045 sales units. So to say the same thing for radio would mean that if you hold TV and newspaper fixed and you increase radio by 1 unit, that means you would go from something like 37.8 to 38.8, you would expect to increase your sales units by 0.188. Now that was the case for positive coefficients. For negative coefficients, it's actually technically the opposite. Holding, for example, TV and radio fixed, for every unit increase you spend on newspaper advertising, you actually expect a drop in sales, and you expect a drop of 0.001 sales units. And I keep using the word units because technically here, these numbers are in thousands of dollars, and the sales could be in units, or the sales could also be in thousands of dollars. But it's easier to think of the coefficients as just relationships between a 1 unit increase of the feature causing this unit increase for the particular label. And if you take a look at our lecture notebook, we actually spell it out in quite a bit of detail for each coefficient. So I'm just going to bring in the lecture notebook briefly. So if you scroll over to our discussion on the coefficients in the lecture notebook, we have here the bullet point description that takes into account in terms of units, as well as in terms of, if you're thinking about it, in thousands of dollars of expenditure. Okay, so that's the way we can interpret the coefficients. Again, positive coefficients, it means you increase the units here, you're increasing the Y label. Negative coefficient means if you're increasing the feature, that means you're decreasing the Y label. And if you have a coefficient of 0, it pretty much means that that feature is actually not really important. So something we could actually observe here is to maybe not even consider advertising in newspapers. In fact, later on, what we could do is just drop this feature completely because our model's not really considering it. A really common student question I get at this point is they think about the simple linear regression model and how at the end we were able to plot that red line against the scatter plot. And they often ask me, how can I create that same plot for this linear regression model? unfortunately, we're dealing with more than just one single X feature, which means I would somehow need to visualize the TV axis, the radio axis, the newspaper axis, and the sales axes. And there's way too many axes for actually plotting this out as a graph. But what I could do in this case is try to just predict off my entire X data set and then just plot out my predictions against the existing data for each feature. This is okay for 3 features, but keep in mind, really any more than this, and it becomes unreasonable to really show this plot. I'm going to copy and paste some code that we've created. So we're going to say here, take the final model and then predict off the entire data set some y hat. So run that for our y hat predictions, and then what we could do then is just plot out these predictions across sales versus TV, sales versus radio, and sales versus newspaper. So this is kind of just showing parts of that regression line. And I'm just going to plot it out here. So again, all we're doing here is we're plotting TV versus sales, our real data points, and then we're going to plot our predicted points against the true TV points. So I can run this, and then I don't get exactly a line, but instead I just get my predicted points against my true points. And keep in mind, the prediction points are in red and the true points are in default blue. So this is kind of the best you can do for comparing visually your actual regression predictions versus the true feature values. Again, it's kind of almost impossible to actually draw a line here because you're dealing with more than just one X feature. You're dealing with TV, radio spend, and newspaper spend. So you'd have to somehow think of a way to map out those axes. So this is kind of the best you're going to get. And really, more than 3 features, this becomes less useful. So unfortunately, due to the limits of living in a 3-dimensional world, at a certain point, we can't really visually plot this anymore, which is why it's so important to have a good understanding of things like the residual plot, which is something we can plot out regardless of how many features we have. Okay, the last thing I want to point out before we move on to loading and saving our model for predicting on new data is one quick note on the coefficients. Recall that for this particular data set, the units of TV, radio, and newspaper all happen to be in the same units. They were all in thousands of dollars, which means I can interpret each of these coefficients in relation to each other. However, for something like the features of a house, where you could have something like square footage and also number of bedrooms, those features are in completely different units. One's in square feet and one's in just a numerical integer for number of bedrooms. For that case, you'll need to normalize the data first before you even start training the model. So keep in mind, in the real world, it's very unlikely that all your features happen to conveniently share the same number of units, which allows for very convenient interpretations of the coefficients without having to do any normalization. Later on, we will be dealing with kind of more realistic data sets where we do need to normalize the data. For right now, it's just a note to keep in mind. Okay, let's talk about model persistence, that is saving and loading a model, essentially our very basic way of deploying a model to the real world. To do this, you need to say from 𝒊𝒏 import dump, load. These are essentially 2 functions that allow you to dump or save the model and then also load it back up. So we can say from 𝒊𝒏 import dump load, and then you say dump the final model, comma, and then whatever you want to call your model. So I can call this final sales model. Let's say final underscore sales model dot 𝒊𝒏. And this is essentially now a trained model file that's going to be saved on your computer that you could then send to somebody. So let's say you send this or you upload it to Google Drive or something like that, and your coworker is then able to download this 𝒊𝒏 file. They should then be able to load it up by creating a variable of their own, saying loaded model, and then they would, from their end, say from 𝒊𝒏 import load, and then they would simply load up that file. So I'm going to load back up final sales model 𝒊𝒏. I run that, and now this loaded model is my trained regression model. So I can actually then call the coefficients off of this one, and notice it has the exact same coefficients as my final model back up here. So this is the exact same model. It's already trained for us. So now you could quote unquote deploy it by sending it to someone else and then having them load it and run it. So for the final test, let's go ahead and predict the sales value for some campaign. So if we're going to predict for some new advertising campaign, let's go ahead and make up a new advertising campaign. Something to keep in mind is the shape of your features that you trained on. In our case, the shape is two-dimensional. There's rows by some number of columns. So that means that our example campaign, so let's go ahead and create an example campaign, will also need to have a two-dimensional shape, which means I'm going to kind of have an outer set of brackets and then an inner one. This is to make sure it matches up with the original data that was trained on. If you don't do it with two sets of brackets, you'll get an error saying the shape was mismatched. Okay, so let's go ahead and say we're going to run an imaginary campaign where we spend 149 units on TV. Then we're going to spend, let's say, 22 units on radio, and let's say 12 units on newspaper ads. So the question then your boss asks is, hey, I have this new campaign we're about to run. How many sales do we expect to get off of this? Luckily for you, your friend just sent you this model that you've already loaded up. So it's time to just type in 149, 22, 12, run this, get your loaded model, and then call predict off this campaign object add. And there you go. We would expect to get 13.89 units of sales for this particular campaign. How accurate is this prediction? You actually have no way of knowing, since this is completely new data that the model has never seen before. We just essentially made it up. So we actually don't know how accurate this is, but we do know that this same model on stuff it's never seen before, more or less will perform with a mean absolute error of 1.21 and a root mean squared error of 1.51. So you can roughly assume this similar performance for our loaded model on new data, as long as the new data is more or less in the range of existing data. Okay, and that's it. We just ran through our entire first machine learning project. We still have a lot to learn, especially when it comes to adjusting models, but we pretty much have gone through the entire steps from reading in a data set all the way to a loaded model that has been saved and predicting on new data. That's the supervised machine learning process. Thanks, and I'll see you at the next lecture.